All right, welcome everybody to our new unit on polygons. This lesson today has got some definitions, a couple theorems, some examples, and we'll get right into it with starting out with some definitions. First of all, a polygon is simply a figure formed by line segments. So you see in my drawing there that you have looks like a five-sided figure, all connected by line segments. The point of connection of the line segments is called the vertex, so you see that there. The segments are called sides of the polygon. And if you can connect two vertices or non-consecutive vertices, so in other words, not next to each other, you have a diagonal of the polygon. So we're going to talk about those in this lesson. So we'll start out by giving polygons some names here based on the number of sides of the polygon. So some of these you probably are already familiar with. Maybe some of them you are not, but we'll start at the top. So three-sided polygon's a triangle. Four-sided polygon's a quadrilateral, so quad means four. Five-sided polygon is a pentagon. The most famous pentagon in the world is a Pentagon building in Washington, D.C. It's got five sides if you've ever seen that building. Number six is a hexagon, or six-sided polygon is a hexagon. The seven-sided polygon is a heptagon. You're probably familiar with an eight-sided polygon. That's an octagon. That's a stop sign. Nonagon has nine sides. Nine and nonagon start with the same letter, so easy to remember that. Decagon has 10 sides, so 10 years in a decade, so 10 sides in a decagon. 12-sided polygon is a dodecagon. And really, when you get above 12, there are names for some of them, but we just normally call them whatever, like a 13-sided polygon would be a 13gon, and so on. Okay, so a little bit more vocabulary. We know some of these words already when we dealt with triangles. So an equilateral polygon is a polygon where all the sides are congruent. An equiangular polygon is a polygon where all the angles are congruent. Now we have a new term for us. A regular polygon is a polygon where all the sides are congruent and all the angles are congruent. So it's equilateral and equiangular would make a regular polygon. Okay, now we got a couple of words, new vocabulary words we got to keep straight here. Concave and convex. On the left side of the drawing there, you see a concave polygon. I like to think of a concave polygon. This helps me remember it as a polygon where one side is caving in. Just helps me remember by word association. Convex polygon then has no cave-ins anywhere in the polygon. And here's a way to kind of distinguish. It's called the rubber band test. And it works like this. So if you want to know whether your polygon is concave or convex, imagine stretching a rubber band around the figure. If you can see any daylight between the polygon and the rubber band, you're going to have a concave polygon, like in this first one. If you could put that rubber band around the polygon tightly and not see any daylight, that's a convex polygon. So when you hear the words concave and convex, you can think of the rubber band test and what you might have as far as a polygon. Okay, so we come to our first theorem. This is a polygon angle sum theorem. I'm going to consider this pretty important. I'm going to read the theorem to you. We're not going to do a literal proof of it. I'm going to give you some examples and show you how it's actually believable without actually proving it rigorously. So the theorem says the sum of the interior angle measures of a polygon with n sides is n minus 2 times 180. So the formula is telling you that if you want to know what do all these angles add up to, inside of a polygon, on the inside now, talking about interior angles, you count the number of sides. So the number of sides is n, and then you put them into this formula, n minus 2 times 180. So let's see if that works for the shape we already know of the triangle. So in a triangle, it has three sides. It's a triangle, and we already know that those angles add up to 180. We already proved that theorem. Okay, let's move on to a quadrilateral. Quadrilateral has four sides. You can divide the quadrilateral up into two triangles if you draw that diagonal. And so the angle sum, so we're talking about these four angles of the original polygon, original quadrilateral, those are going to be found by taking the number of triangles that fit inside there times 180 for each triangle. So 2 times 180 is 360. So this triangle would have a sum of 180 degrees, and so would this one. So you just count how many triangles you can make out of that polygon and multiply that by 180, and that'll be what those interior angles add up to. It's called the interior angle sum. So as we go through these examples, see if you see a pattern. Pentagon has 5 sides, as we mentioned. If I can draw the diagonals from one point, this time I have 2 diagonals, and I've made 3 triangles. So each of those 3 triangles contains 180 degrees. And so if I want to find that interior angle sum, this time I'm going to take 3 times 180 is 540. So 540 is what those 5 interior angles add up to inside the pentagon. Let's do one more and then we'll talk about the pattern. Hexagon has 6 sides, so this time if I draw the diagonals from a single vertex, I have 3 diagonals, and I have divided the hexagon up into 4 triangles. So 6 sides, 4 triangles. Each triangle again has 180 degrees. So if I want to find out what all the interior angles that hexagon add up to, it's 4 times 180 is 720. So I hope you noticed as we did these 4 examples that the number of triangles you can divide the polygon up into depends on the sides. So in every single case, the number of sides minus 2 is the number of triangles. So here we had 6 sides, 4 triangles. Let's back up a little bit. Here we had 5 triangles, 5 sides, 3 triangles, so always 2 fewer triangles than you have sides. Here we had 4 sides and 2 triangles. So if you want to find out what the interior angle sum is for any polygon, all you have to know is how many sides it has. So if it has n sides, subtract 2 from that. That's how many triangles will fit inside that polygon. And then, of course, take that number of triangles times 180 for each triangle, and that's what are going to be all those interior angles add up to. Okay, so I have an example for that right here. It says find the sum of the measures of the interior angles of an octagon. So we know an octagon has 8 sides. Let's pull out that formula we just kind of showed you. The sum of those 8 angles is n minus 2 times 180. If you got 8 sides, you have 6 triangles inside. Just subtract 2 from the number of sides. Each triangle has 180 degrees, so 6 times 180. The inside angles or interior angles of that 8-sided polygon add up to 1,080 degrees. Now, read this one carefully. It says find the measure of each interior angle of a regular nonagon. So this is really a 2-step process here. We're going to find out what do those 9 angles add up to in total, and then we're going to divide that figure by 9 because it says it's a regular polygon, a regular nonagon. So that means all the angles are congruent. So if we know what they add up to, we just divide by how many there are, and that tells you what one of them is. So the sum of those 9 angles, according to our formula, is subtract 2 from the number of triangles. So we have 9 minus 2. We have 7 triangles inside that nonagon. So 7 times 180 is 1260. So that's what those inside angles of that nonagon add up to. Now, because we said that the nonagon is regular, that means it's equal angular. All angles are congruent. So we take what those 9 angles add up to and divide it by 9 for 140 degrees for each one of them. Okay? So that's the polygon angle sum theorem. And the last theorem we have for our notes today is the polygon exterior angle sum theorem. So we had exterior angles earlier in the year when we talked about the exterior angle theorem for a triangle. And so what you get an exterior angle when you extend one side of the triangle. So let's say I extend this side of the triangle, and that I've formed an exterior angle with the adjacent side. So let's say I just measured that and I got 81 degrees. So I'm going to do that for the other 2 vertices. So let's say this time I extend this side of the triangle, and again I've formed an angle with the adjacent side of the triangle. So let's just say I measured that and I got 132. All right, let's extend this third side of the triangle to form another exterior angle. Let's say I measured that and I got 147. So this theorem says if I add up those three exterior angles, so 147, 81, 132, if I add all those up, I'm going to get 360. All the time, and it doesn't matter how many sides your polygon has, and it doesn't have to be regular or not, it doesn't matter. If you take an exterior angle, one at each vertex, and measure them and add them up, they're going to always add up to 360 no matter how many sides you have in your polygon. I'm going to do that for one more problem, and then that'll wrap up our notes. So here's another polygon. And let's do the same thing. Let's extend all the sides. So I'm going to extend this side. Let's say I measured that and I got 41 degrees. Let's extend this side so I have another exterior angle. Let's say I measured that and I got 55 degrees. Extend this side. This time I got 110 degrees. Okay, I've extended three sides. I got two sides to go. Let's say I extend this side. And I measure that exterior angle. That's 43 degrees. Then I got one more. Let's say I extend this side. And I measure that exterior angle. That's going to be 111 degrees. So the polygon exterior angle sum theorem says if I take all those and add them up, so I got the 111, got the 41, got the 55, the 110, and the 43. So if you took out a calculator and add those up, I'll spare you the trouble. That's going to add up to 360 all the time. So it doesn't matter how many sides the polygon has. If you add up all the exterior angles going around that polygon, one at each vertex, then they will add up to 360. So that's the polygon exterior angle sum theorem. Okay, we had a lot of material here to kind of wrap it up here before we stop here. We got definitions of what a polygon is, and it's made up of sides that are line segments. The sides come together to vertex, and it has diagonals inside. Some of them do, most of them do, except for a triangle. We had an equilateral polygon, which all the sides are congruent, equal angular polygon, where the angles are congruent, a regular polygon, so get to know that word. Regular polygon is equal angular and equilateral. We talked about a concave versus convex polygon. Remember, the rubber band test tells you whether that polygon is concave or convex. We had, I forgot, we had names of the polygons based on how many sides they have. So 3 sides is a triangle, 4 sides is a quadrilateral, 5 sides is a pentagon, 6 sides is a hexagon, 7 sides is a heptagon, 8 sides is an octagon, 9 sides is a nonagon, 10 sides is a decagon, 12 sides is a dodecagon. Anything greater than 12 sides is called an n-gon. Okay, so we had that, and then we had our formula for finding the interior angle sum of any polygon. That is, you count the number of sides in the polygon, subtract 2. That'll be the number of triangles that fit inside. Multiply that number by 180 for each triangle, and that'll be what those interior angles add up to. And finally, we had the polygon angle sum theorem, which said no matter how many sides your polygon has, if you go up and add all the exterior angles from that polygon, one angle at each vertex, then they will always add up to 360. All right, so the assignments are posted in Google Classroom, so let's get some practice. Enjoy. Thanks. Bye.